Okay, so welcome everybody to the class on advanced machine learning or something like that. So this, what we're going to be covering today, actually, could somebody please close the door? Is going to be a little bit more advanced. So this is advanced at the point of where you'll actually see a couple of results that we got in the last year or this year. But the ideas behind it are sufficiently simple that you can just use them regardless, and you'll actually do pretty well by using those ideas. So the first thing to look at is basically when you want to build a large system, how you actually write multi-core code. Okay, so let me ask a first quick question. Who's written multi-core code so far? Okay. Well, that's, I think, a proud maybe 15% of the audience. Okay. Who's used MATLAB before? Okay, so so that means you have written multi-core code. Except that you probably didn't notice it. So first of all, I guess nobody should be surprised that there are more than one cores in your laptop. Who knows how many cores your laptop has? Okay, if you don't, you should find out. Who knows how fast your laptop is? Okay, again, you should try to find out. So here's why those things matter. If you write code, and inevitably your code will be slow, because all the code is, it's never fast enough for what you want to do. Let's say you're working for an IPS deadline or ICML or KDD or whatever, then you have two options. Either you pretty much get all the experimental settings and everything right straight out of the box, which is not going to happen, right? Or you need to iterate. Now, if your code takes a day to run, then you can basically make changes maybe 2-3 times a day, assuming that you have 2 or 3 computers, right? But that may not be enough, right? Because then you make a small change, you spend an hour on that, you start the code again, and then maybe you can watch TV for a day or agonize over the fact that your code isn't running or that it's not working. It's another way of multitasking. So, yeah. So basically, the reason why you want to write multi-core code is because by now, the speed on a per-core basis isn't actually increasing that much anymore. It's going up by 10-15% per year. But the core count is still increasing. So for instance, by now, for I think $4,000 a piece, Intel will happily sell you an 18-core processor, which, as it so happens, has, well, 36 hyperthreads. So I guess everybody knows the difference between hyperthreads and cores, right? Basically, hyperthreads are just like fake cores, and for all practical purposes, you can treat them like one, but they don't scale perfectly. So if you're running scaling experiments and you increase the number of threads and so on, then at some point, your code will probably top out at, if I have this fancy Intel 18-core processor at about 18 threads or maybe 20, only if my code is really inefficient will I need a lot more. Okay. So if you want to know more details, you should read up on AnandTech and other sites, which explains this in a lot more detail. Okay. So hyperthreading is good, but you don't really have real cores there. Okay. The thing why MATLAB is actually using multi-core is because if you're doing any linear algebra operations, so like, I define some matrix A, I define some matrix B, and then I have something of the form, C equals A times B, then MATLAB will not just use a single core, it'll actually go and take each of those matrices, block them neatly together, and then do the multiplications and write them over here as appropriate. And there's highly optimized code for doing this. Okay. So the morale of that story is actually never ever write your own linear algebra code until you really know what you're doing. You will know what you're doing once you start thinking about the details of this, right? So don't think about writing your own linear algebra code. Use either MATLAB, which is just fine for linear algebra, or Octave, which is fine if you compile it right. Otherwise, it won't be. Or then you can use something like BLAS and LAPACK. And this is neatly hidden, for instance, in C++ in a library called Eigen. Strongly recommend you to look at that. Okay. So that's all fine if you're doing, let's say, spectral methods, or if you're doing PCA or other things, then yeah, MATLAB will do. If you don't, then MATLAB won't do. And so you need to think a little bit about how on earth am I actually going to write multi-core code. And so one of the key issues with that kind of code is that, well, if it runs on multiple cores, please don't sit there, otherwise it gets unplugged. There's a seat just right behind you. Thank you. There's seats over there. Yeah. So then you need to address the issue of, well, you know, if I'm doing this, how will the various processes actually talk to each other? And usually the purpose of all of this nice these algorithms is to estimate some numbers. How do I actually jointly update a number, right? So let's look at a very, very simple case first, because this is sort of kind of prototypical for what we're going to do. The simple task is I have a bunch of numbers, x1 up to xm, and I want to compute their average. And I want to map this into 1 over m, sum over I going from 1 to m, xi. Okay. So how would I solve this in parallel? With multi-core. How would I do this? So I have maybe a million numbers. Actually, make it a billion, because for a million it's almost not worth bothering. How would I do this?
Split the sum into several sums, which are computed in parallel.
Exactly. Perfect. That's exactly the right answer. So take that entire sum, break it into, let's say I have 16 cores, and each core gets 1/16 of the data. You happily compute partial sums there. Then in the end, you hit the barrier. This barrier is basically wait until all the cores are done, right? And then sum everything up. So what we've just seen is actually two important parts in that code, namely parallel execution, which runs independently, and then at some point a barrier at which basically all the threads have to hit, and then you just can happily sum everything up. Okay. C++ by now actually provides very nice primitives for that. Also look at Intel threading building blocks, so Intel TBB. But C++ 11 also has a whole bunch of nice features in there. Right. Also OpenMP. Don't bother with pthreads until you really know what you're doing. It's very painful. Okay. So basically what was just described, namely compute partial sums and then add everything up. Then, basically go and update this and then write it to disk. Okay. So this works very nicely if, for instance, all the data fits nicely into memory, or if I can, easily proportion things to individual cores. If it doesn't, in other words, if I want to have something that's asynchronous, then what could I do? Well, so imagine I give you all some task to do. Let's say some, programming assignment or whatever. And because you have more or less sleep, or because you're a more or less proficient programmer, it will take you more or less time to actually finish this task. So now if I say, well, everybody has to wait until the last person is done, there will be a lot of people very unhappy, namely, well, those who are really quick will just sit there and twist their thumbs or, play a video game. So that's not good. So instead, what you actually want to do is you want to have asynchronous processing. The asynchronous processing could be, for instance, that fish simply sits there, and whenever somebody is done with their task, they will give fish, well, the assignment, and she'll incorporate it into the total workload, and so this way you can get out of the way. Even better, she might actually come back to you and say, well, oh, you were so quick. As a reward, you get extra work to do. Right? This is then a dynamic load balancing. In other words, this is adjusting based on the speed and so on of the individual processors. Okay. So that way, that's pretty much what I wrote here. Right? So the individual processes, well, they execute whatever they do on the data. So I have one thread that does nothing else but just read from disk or from network or wherever. I have a whole bunch of processes that actually process the data, and they generate updates to some common state. So those updates could be the partial sums. They could be estimates of how my parameter vector for, let's say, a classifier or regressor, whatever needs to be changed. And then I have a separate thread which actually goes and writes this back into local state. So the key benefit that we have with multi-core is that actually there's a shared memory. So that's a huge deal because it simply means that we can go and, well, each core can immediately read what everybody else has. Right? That's actually a big benefit. Once you go to multi-machine, that shared memory aspect is gone, right? So unless you build really super high performance computers that are custom built, each machine essentially has its own memory, and then you need to do extra things to actually synchronize things. Okay. What I'm completely sweeping under the rug here is the aspect of whether this thing will actually converge, right? So I didn't discuss at all whether this makes any statistical sense, whether it makes any sense in terms of optimization. I'm assuming that that's okay anyway. And by the way, this is the part where you will probably spend a non-trivial amount of your time when you prove that one of those algorithms is sensible. So most of your time when you solve any of those problems is going to be to implement it, and then secondly to prove that it's not crazy. The good thing is that in most cases it's not crazy. So there's a very nice paper that just recently came up on arXiv by John Ducci. I forgot the title, but it's basically one of his recent multi-core, multi-machine parallel processing papers. And the bottom line of this is almost everything works. So it's a pretty nice paper. Okay, good. So I think I've belabored that point of just the overall template of multi-core a lot. I know this sounds utterly trivial, but you could come up with ridiculously complicated ways of synchronizing things. And occasionally people write papers and they try to prove things for very complicated things, and they think they do it mostly such that they can make life complicated. But this is way easier to design and to debug, because if you have multi-threaded code, then it's going to be way harder to find out whether something goes wrong and why it goes wrong. Okay. Any questions so far?
How is this related to machine learning?
Well, how's that related to machine learning? Well, if you're a theorist and you just care about uniform convergence bounds, then you can fall asleep for the rest of this class. You don't need it. Okay. If you're a theorist who cares about efficient algorithms, then you should not fall asleep during the rest of the class. Because the thing is that because basically processors per core aren't getting any faster. And if at some point in machine learning we usually try to design algorithms that actually work in practice, right? And if I have a lot of data, then I will need multiple cores to process this. And if I don't have an algorithm that can efficiently run on multiple cores, then I'm dead. So this is why you actually do care in machine learning about this. So let me give you an example. Recommender systems, right? So now there's a machine learning example, right? And for calibration, if you do this poorly, there's a company whose services you may have used, and I cannot say anything more specific than that, but basically for something that you can easily solve in about 2-3 hours on a single machine, they spend a Hadoop cluster with 1,000 machines on it. So I actually had a conversation with some of the engineers, and they went like, well, that's job security. Okay, now I'll tell you how to do it with a single machine without the 1,000 machines Hadoop cluster. So I guess everybody's heard of recommender systems, right? So this is basically if you use Netflix, if you use Amazon or whatever, the idea is basically, based on your past preferences and based on everybody else's preferences, what else would you recommend? And a very simple model might be one of the form where you have a profile vector. Let's say the movie has a profile vector, and then you have biases. So there might be a user bias because maybe you're a horribly grouchy guy and you don't like any movie at all, so you complain about everything. On the other hand, maybe that movie is really fantastic and everybody likes it. So let's say Life is Beautiful. Well, it's commonly agreed that it's a great movie, so even if you're a grouch, you're still going to like it. And then there are specific preferences. Maybe you only like Japanese anime and nothing else, so VU is basically going to have components only that are positive for that and negative for the rest. And then the movie is going to have, its own attributes. Okay. Now, what people typically use as a means of calibrating how well your algorithm works is something like a least mean squares loss. In other words, I compute the difference between what my estimator does, namely this is what I'm estimating, and this is what the rating really was. Let's say it's from 1 to 5 stars. Can somebody tell me why this is actually a stupid idea to use a least mean squares loss? Yes?
We often don't really have the why very well. Like usually the best way to look at is just to see what people have watched. Most people don't bother reading. So.
Okay, so you're way ahead of the curve. Basically what you're saying is we should actually do proper user modeling and to look at, conditioned on what the user saw, what they're doing. This is, that's the really, really, really deep answer. Can somebody give me a slightly more shallow answer? By the way, awesome insight. Maybe the right half of the room. Okay, why is having just the y's, basically just using least mean squares on the y's, not a great idea?
You can go outside of the range, so it's between 1 and 5.
You could go outside the range. You're already on the right track. So in other words, if this is a 5-star movie and I give it a 6 or a 7, well, that's still okay, right? Because, the user thought it's a great movie. I also think it's an awesome movie, so that's fine. You're on the right track, but there's a slightly more subtle reason. Okay, question. Who's watched Barbarella? Okay, so see, nobody's really watched it, right? It's a shitty movie. You only need to read the abstract and then basically, see the trailer. It's a shitty movie. Okay, why does this matter? Well, Barbarella is probably a solid 1 star. Now, given that this is a solid 1 star and you have probably very other preferences, is it really important that the system figures out that you really don't like Barbarella? Or is it okay if it says you don't like it? Right? In other words, how bad is it if my system estimates Barbarella as a 2-star rather than a 1 star? How bad do you think that is? Who thinks it's really bad? Who thinks it's not bad? Okay. See, so in other words, getting the irrelevant movies wrong, slightly wrong, is not very bad. It's not very bad, at least not until they start messing up the actual ratings. Right. So if this is my scale of movies, and these are the ones that I really care watching, then whatever happens over here doesn't really matter, as long as none of them ends up here. This is where it really hurts. So if all of a sudden Barbarella becomes a 4-star, this is a problem. But other than that, it doesn't really matter whether it's a 1, 2, or 3-star. Okay? So in other words, we actually should have a loss that takes into account the relative ordering, right? So those things are called ranking losses. This is essentially, if we were to teach a class on recommender systems and user modeling, we'd go into a lot of details there. But since we don't have time for that, well, okay, we'll just do the very simple thing and do least mean squares. Okay.
But we could use Hoover's loss and then it would be not sensitive to outliers, right?
You could do that. That would make things slightly better.
Because we also don't want movies which are 4-star to end up at 1-star.
Mm-hmm. So, well, actually, okay, what's worse? Is it worse that I recommend you Barbarella, or is it worse that I miss Life is Beautiful?
That you miss Life is Beautiful.
Actually, it's the other way around.
Actually, the other one. Yeah.
So imagine you
They're
go.
at the top view. That's
Yeah.
what you presented.
Yeah, exactly. So imagine you go to a restaurant, right? And they serve you a really disgusting dish. Well, that's really bad. On the other hand, if you go to a restaurant, they don't have your favorite dish, but still a whole bunch of other tasty dishes, you'll probably be okay. So there's also asymmetry in the loss, right? So because we don't necessarily care about recall quite that much. I mean, yes, sure, if I do this, then I lose on discoverability. But what you can see from this very simple example is that actually losses are highly non-trivial and structured in practice. And you need to think fairly carefully about this. Mind you, what I'm summing up here in about a discussion of about 10 minutes, this took the recommender systems community maybe about half a decade to figure out, right? So while this all sounds really pretty obvious in hindsight, it actually took a long time until people had it figured out. So don't feel bad about not guessing everything right from the beginning. This is hard stuff. Okay. Well, be that as it may, since Netflix decided that this is the loss function that they would use to measure performance in the Netflix contest, well, okay, let's just stick with this. Okay, now, how would we actually go and optimize this? One thing we would do is, for instance, also add some least mean squares regularization. So in other words, we just want to make sure our coefficients are small. And once I do this, I can then go and just perform simple stochastic gradient descent. So this is about as simple an algorithm as it gets. I basically take a user movie rating triple. I compute the estimate. I look at the true score, take the difference. So that's basically what's happening here. And then I go and update the movie and user parameters appropriately. Okay. So that sounds kind of straightforward, right? And I shrink everything a little bit, but that's pretty much it. So this has been known for pretty much 1 to 2 years after. So I think within 1 year of the Netflix contest coming out, somebody suggested this algorithm and it works amazingly well. And it's fast. And it's way, way faster than alternating optimization because, I mean, as you can clearly see, this problem is convex in V given the U's, and it's convex in U given the V's. And by the way, this should be, well, a W, right? So there's a typo in the slides. So this algorithm should be really fast and cheap to implement. We could actually hand this out as a programming assignment and you'd fairly easily ace it, right? This is simple code, right? It's 2 lines. You can do that in MATLAB. Now this algorithm should be really cheap. But let's just see how long it takes. So who knows the difference between latency and bandwidth? I guess everybody does, right? Latency is how long it takes me to get something. Bandwidth is how quickly I can get it at a sustained rate. Now, main memory has those two characteristics too. More to the point, the memory latency is going to be in the order of maybe 100 nanoseconds. Well, it sounds like a small number, but I do that a lot, so small numbers still add up once I use it a lot. But it actually has a fairly high bandwidth. It has between 60 and 100 gigabytes per second bandwidth, so the specifics depend a little bit on the latest generation of the processor that you have, your memory chips and all of that. The important thing is that bandwidth has actually gone up drastically over the past decade. It's gone up by maybe a factor of 100 at least. Latency has hardly changed at all. Part of the reason is that for latency, the processor basically has to go and tell the memory chip, hey, by the way, I want to read over there. And then the memory chip gets its stuff ready, and then it could actually send you not just this one byte, but it could send you an entire slew of information. Especially if you have, two memory banks and all of that, you can actually read from both at the same time, and you can do all sorts of fun things depending on what your processor looks like. Right? So if we do a little bit of, back of the envelope calculation, what you can immediately see is that, well, if I want to go through the entire data and I have m observations and have d dimensions in the factors, and we're just ignoring the constants here, I need order m times d bytes to read and also write. Because I need to read all those vectors in, I need to write them back to disk. On top of that, I need to look up order of m random locations in memory, because basically for every user movie pair, I need to look up the user vector, I need to look up the movie vector. So that's going to be the thing that really hits us for the burst. Sorry, for the random memory lookup. So if you do the calculation for 60 gigabytes per second memory bandwidth, let's say we're using doubles, and Netflix has about 100 million observations, 2048 dimensions, 30 iterations. Well, this takes about 1.5 hours, just based on the memory on its own. So note that this calculation here completely ignored what processor I have. Well, it didn't entirely ignore it. It still took it into account in terms of how fast it can talk to the memory. But other than that, CPU speed didn't even matter. Even just getting the stuff into the CPU and then writing it back out takes that long. So now here's a fun thing. We actually managed to squeeze this by a factor of 8. Okay. Now you would say, well, that's crazy engineering, right? I mean, why would I bother? Well, a factor of 8 actually matters, because if all of a sudden rather than maybe 100 machines, you need 10 machines, well, you can probably do it in your professor's cluster, right? He probably has more than 10 machines somewhere in his cluster. Whereas with 100 machines, you probably have to go to AWS and do all sorts of other things, right? So that's why it matters that you can actually have things, if you get an order of magnitude speed up. For 20-30%, don't bother. For an order of magnitude, do bother, right? So who thinks they might have an idea as to why you can do it faster than what the memory suggests?
You fetch the data from the memory and use it more than once.
You're on the right track. That's in a nutshell what it is, but what exactly do I use more than once? Because
to do the iteration, you can't wait for everyone to finish the iteration.
No, but remember, this calculation here was regardless of the number of cores. This was just the memory interface. So how can I do things faster than the memory interface?
Can you ensure that all the data appears together in the memory?
That might cut down on the latency, right? So that way maybe I can cut this down.
Do you get the exact same result?
Yeah. So here's what happens. If you think about it, the main memory isn't the only place where I can store stuff. Where else can I store things?
Cache.
Exactly. So, and there are actually several levels of caches, right? Level 1, level 2, level 3. And they're basically of different size and different latency and bandwidth and so on. And that's the solution of the puzzle. So if you look at the Netflix dataset, then you can see that most of the movies don't really get a lot of ratings. And there are a few movies that get all the ratings. It's just like with papers, right? There are a few papers that everybody cites, and then the rest nobody cares about. So if you look at your own publications, you'll probably see exactly the same power law. And sometimes it's very frustrating because you think your really cool paper sits up there, but nobody cares. Right. So what really happens is that there are only a small number of movies that really are very frequently accessed. And so therefore, if I can keep them close to the CPU in the cache, then I can essentially beat the main memory barrier. Okay? That's basically what you do. So the first thing is you actually change the algorithm slightly. You go and stratify by users. So in other words, you process all the ratings for any given user at a time. Well, why is this desirable? Because this basically halves the memory pressure. Because once I have this parameter for that user in memory, I don't need to read and write. I just keep it in the cache, and then only afterwards I write it back out. So this is actually changing the way how we process the data slightly, but it's something that's actually very much in line with how you would be storing it anyway, so it's not a big deal. The second thing is you want to make sure that the frequent movies actually stay in the cache. Okay? And to some extent the operating system and the microprocessor, they all help you with that, so this is okay. The third thing that you need to worry about is something called fault sharing. Who's heard of fault sharing before? Okay, wow, awesome. One person, but awesome that you know about it. So here's what happens. Let's say I have two processors, P1 and P2. And they both have a cache. And then underneath there sits a main memory. So these are actually in different sockets. So for instance, if you have a high-end server with two sockets, right? Now, what can happen is that some location in memory is actually cached in processor 1 in its cache. And as long as processor 1 only works with that, that's fine. And at some point it says, okay, well fine, I'm done, and it pushes it back out. That's okay. Now let's imagine that processor 2 at the same time also decides it would rather like to work on this. Right? So now processor 2 realizes, and well, realizing with that it means that Intel or AMD or whoever built hardware to detect this, that actually this isn't the latest version. So what it now does is it says, well, okay, fine, I badly need it, so let me send a request to processor 1. Now processor 1 stops and drops everything that it's currently doing. It then immediately goes ahead and writes things out to main memory, where it then is being read into processor 2. So this is like if you're sharing a pen with a friend, right? And you both need to fast and furiously, write your homework. So while maybe your friend's using the pen, you then need to tell her, well, hey, drop everything, stop what you're doing. Well, put the pen back, you grab the pen, you write. All the while, she's waiting for you to return the pen. So now, all of a sudden, you've essentially halved the productivity. And that's exactly what happens here. So not only is your own processor waiting, you've also blocked the other one. Now, if you have a 4-socket system, it gets worse, right?
That's why we have shared cache on
That's
that thing.
so. If you have a multi-core, and the multiple cores are within the same processor, that works. If you have a 2-socket system, it doesn't work, right? So a lot of high-end systems have more than one processor socket. And that's exactly where this comes back to bite you. Make no mistake, this is a factor of 2 quite easily if you fix it. So if you're serious about this, at least do a Google search about false sharing, read the Wikipedia page, and be cognizant of it when you write your code. Because a factor of 2, well, can make or break a paper. Right? Now, if you do all of those things, you get actually very, very cache-efficient code. So a 3% cache miss rate is, so that's on level 1, and 1.5 on level 3, are pretty awesome numbers, especially if you compare it to what some other highly optimized codes take. So GraphG, by the way, made one key mistake there. They basically go and partition the users and movies like a checkerboard and then process each of those blocks separately, whereas what we do is probably closer to Venetian blinds. So because you basically process one user at a time. Well, let's actually see how this translates into numbers. So this is something that Ziqi Liu implemented. This is basically our solver. This is GraphLab. Well, that's basically a GPU code. So what you can notice is, we're beating a GPU code by a factor of 2 or 3. Now, could you do the same thing on the GPU? Almost certainly you could, but we didn't look into detail too much into bitmap to know whether they're already using some of those tricks. But you could probably bring that curve down back here. But what this shows you is that by being smart about the memory subsystem, you can actually write very, very efficient codes. And yeah, so, multiples, well, that's where you care. The other thing where this really matters, if you look at this is GraphG, this is us, you can see that this code actually converges a lot faster. And that has a lot to do with the fact that if I have this checkerboard-like partitioning, then my solver, while it's solving this block here, and here, let's see, here are the movies, here are the users, doesn't actually do any updates on those movies relative to this or that, right? Likewise, it will only perform those updates in these larger blocks, whereas otherwise, if I take one row at a time, it will actually mix the information about different movies much more efficiently. So while both algorithms are convergent and all of that, it actually matters how you partition your problem in terms of practical convergence. So,
but when you stratify by users, don't the STD updates depend for different processors? How do they communicate that?
okay, so you basically asynchronously just update Hogwarts style. So you don't even lock. And if they overwrite each other, be it so. So it's about as reckless as you possibly can be. So, and there's some analysis that you can make that this is okay. So essentially, if you think about why this works, well, when we're trying to solve a statistical estimation or an optimization problem, we start off with some rather horrible parameter anyway, right? So it's really wrong. I mean, after all, if we already knew the answer, why would we want to optimize, right? And so I'm taking steps towards optimality. Now what happens is that so it's a convergent algorithm, right? Ultimately, if I run it for long enough, it'll converge to at least a locally optimal solution. Now, if I add some inaccuracies due to log-free updates and doing all of those things, yes, I'm going to introduce a small amount of extra error again. But as long as I can prove that this small amount of extra error is less than what I'm getting through an overall convergent algorithm, I'm still in good shape. Okay. So this is basically why you do that. Okay. So I know this is going into a lot of really excruciating details, but I think it's actually important that at least once in your PhD you think about that, and if it's this class, that's okay. So I don't mind spending this class on these details, because there's nothing worse than writing really horribly slow code that's orders of magnitude slower, and sometimes very smart people do that. So for instance, yesterday, paper came up on Archive about how to do essentially distributed deep learning using Spark. And it's co-authored by some of the biggest names in machine learning. I'm not going to mention their name now, but we all know who they are. And the unfortunate thing, and they make a big case for why this solves all the distributed deep machine learning problems efficiently. Unfortunately, that approach is more than an order of magnitude slower than something much more sensible. Okay, so it's probably about a factor of 20 or 30 slower. And it doesn't converge very well, and it has lots of other issues. So sometimes even very, very senior people who I admire a lot fall into this trap. Okay, so read the paper, and then read the MXNet paper and compare the numbers. And yeah, at some point at NIPS I'll probably have a short conversation with some of those. Okay, so we've already talked a little bit about hardware. This is just some more background. Yeah, you might as well look at that at some point, but basically, so this is from Jeff Dean's Stanford slides, so he taught a class on this. And essentially, what this tells you is that in a server center, stuff can go even more horribly wrong. Don't worry about the specific numbers, but basically, shit happens a lot. Now, if you use AWS or whatever, all of this is hidden from you because, well, they actually have a nice system. Likewise, Google Compute Engine and all of that. But just bear in mind that behind the scenes, a lot of things are going wrong. Okay. Now, this is something that you should probably look into at more detail. Numbers everyone should know. And this is a nice visualization, and just do a Google search on numbers everyone should know, and try to find a version that's reasonably current. Because Jeff Dean put that slide up in, 2009, and then, So it gives you a bit of a calibration of how long it takes to do various things. Now, why do you care? Well, basically, if I have a choice between my algorithm doing something here or there, right, then it's very clear that this is much more desirable, right? Now, you care about it because if I have an algorithm that has a worse polynomial order, maybe it's n log n rather than order n, but each of the steps is a few orders of magnitude faster, then yes, you should use the algorithm that's theoretically slower and in practice much better. And the short summary of all of this is, the further away you have to go to fetch data, the longer it takes, exponentially longer, right? And yes, we've fallen flat on our face with similar things like that as well. Basically, when you start thinking that, well, okay, here's an algorithm that's log linear rather than quadratic, so therefore it must be better in practice. Turns out it's not in some cases. Okay. Yeah. So why do you need more than one machine? Well, because we have a lot of data. And I strongly urge you to do at least one internship somewhere in Silicon Valley. Make sure you don't get abused as a code monkey. I know this sounds kind of obvious, but make sure you know who you'll be working with. Okay, I see that every year, maybe about 5 to 10 students bright PhD students from CMU end up just writing code and not learning much. So make sure you're not one of them. So be choosy about the project that you'll work on, but make sure you go to Silicon Valley at some point and you spend 3 months there and just actually work with the scale. But basically, what we get is we have billions, hundreds of billions of documents. You can actually get about 10 billion by using the Amazon Common Crawl. You might have between 100 million to 1 billion users. So Facebook recently had over 1 billion daily average users for a month. That's quite impressive. There are probably over 1 million days of videos on YouTube and over 100 billion images on Facebook. So there's a lot of data. But realistically, I probably can't process more than a terabyte per machine per hour. As a matter of fact, if I process a terabyte per machine per hour, my code is already pretty good, right? But since we have a lot more data and I need results, within hours as opposed to within weeks, I need to write something that's multi-machine. On top of that, the parameter space is often also way too big for a single machine. So for instance, if I want to personalize content, so let's say Facebook wants to, do personalized recommendation, then you need, on a per machine basis, on a per user basis, you need actually some parameters, what you like and what you don't like. So you can't store it on a single machine. And so what this really means is you need to process on many cores and many machines simultaneously. Okay, this is why you care about multi-machine. Yes, this is part of machine learning. I know this is the engineering side, but there are actually lots of really nice, theoretical questions in there. Okay, I don't think I need to go much more into detail about cloud pricing. The key point is that if you use something that Google calls a preemptible instance, or that Amazon calls a spot instance, you will save a lot of money. In Google's case, it's maybe a factor of 3. On AWS, it can be a factor of 6 or 7. And on AWS, you have to play the fun game about how much do you exactly bid for spot instances. And in Google's case, it's just, okay, that's the price for a preemptible one. And they can kill you any time they want. You don't have to pay for the last hour, which is actually kind of cool. And you know that you will be killed within 24 hours. In some cases, this may actually be desirable. Can somebody tell me when it's desirable to have many machines over and over? Okay. What happens when you get a new machine? Well, okay, sure, you need to set it up, but you also get a new IP number. Okay. Why would I possibly want to have lots of IP numbers and lots of different IP numbers fairly quickly? Any idea? Okay. Well, if you want to crawl data, if at some point you want to do big data, you will probably have to crawl it on your own because they won't give it to you. So let's say I want to crawl Instagram or LinkedIn or Flickr or Yelp or whatever. They will usually let you do a few requests and at some point they'll throttle you. And they'll throttle you based on the IP number. Now if you get a new IP number every 1, 2, 3 hours, right? This is like a legal botnet. Okay? And this way you can actually crawl large amounts of data very cheaply, with you actually using the fact that you have those unreliable instances as a virtue rather than a problem. You then want to design algorithms that actually very easily scale with varying numbers of unreliable machines. And again, simple is best in this case. But other than that, this can actually be a virtue. So, key questions? Well, if we have machines that can fail, well, what actually happens to the data? And how do we keep the data local to wherever we process it? And how do we partition the jobs? And how do we do load balancing if some machines are occasionally slow or not? And then is it really a flat topology if I have 1,000 machines? Well, probably not. So the gold standard of what you might want to aim for is this. So symmetric, no master. So basically, there is no dedicated machine that controls everything else. Because usually if your master fails, you're dead, right? Dynamically scalable means I can add or remove machines as I want, and the system keeps on running. And, well, this is sort of essentially a corollary of that, right? Well, except that here I could say, well, I actually do something explicitly to add or remove machines, whereas there, somebody can go ahead and kill them. So if I have an algorithm that can deal with, random machines being killed, then I immediately have a scalable algorithm, right? Because basically then it already rebalances. Okay, so now let's look a little bit at math again. So who knows what a hash function is? Okay, cool. That's actually more than I thought. So a hash function is, for all practical purposes, a random number generator. Except that it's a random number generator which each time I feed it the same argument, it produces the same random number. Right? Which is actually extremely useful because rather than storing random numbers, I can just look up the same key again. So for instance, if I ever needed to store a monstrous, Gaussian random matrix, and I run out of memory, instead of that, I could just use a hash and then turn the corresponding hash value into a Gaussian random number. So this can reduce memory footprint drastically. And so, of course, the dumbest thing is I just actually compute a random number and then store it. But the smarter way is, well, I just use something like, for instance, member hash, and I'm done. Okay. So the idea is I want to have something that, is uniformly distributed over the keys. On top of that, for two different keys, the probability of collision should be 1 over the key space. That's a two-way independent hash function. If I have 3 keys, then that should be, 3 ways independent hash function if one of those properties happens. In practice, for the analysis, we can deal with ideal hash functions, and I strongly urge you to do that, and unless you're David Carger, who is just brilliant enough to hammer through lots of highly technical proofs for 2 ways independent hash functions. So. He's a brilliant computer scientist, essentially, who, amongst other things, does load balancing, but he also occasionally writes machine learning papers. So, how can we go and use this to allocate data over machines? Well, one thing that I could do is, because I want to have a mechanism which does this allocation regardless of the size of the machine pool, right? So what I could do is I have this machine pool, M, and I compute the hash of the key and any of those machines in the machine pool. And then I pick the machine for which the hash of the key and the machine ID is smallest. So this will, of course, give me a mapping from keys to machines. Furthermore, since I have this ideal hash function, I can immediately see that, well, this will give me a uniform distribution. Because for any given key, there's no specific machine which should be preferred. And with probability 1 over m, it's going to be any of those machines. So this is kind of nice, because now I have a load balancing mechanism which tells me exactly which data goes to which machine for any data, for any key that I could have thought of. Okay. Now, the other thing that's really nice is if I now add or remove a machine. Okay, let's think about it. So let's say there are some keys here for which this particular machine, won all the contest. Now, if I remove, so first of all I know that it's only a fraction of 1 over m. well, an expectation of the keys that actually go to this particular machine. Now, if I remove this machine, for any given key, well, again, it's uniformly distributed over the remaining remaining m-1 machines. So therefore, if one machine dies, the rebalancing is about as nice as I could possibly have it. Furthermore, if I add a machine, again, it steals a fraction of 1/m from all the other machines. So this is as gentle as possible for the load balancing. There's, for instance, a piece of code that's called memcached, which does this quite nicely. It's also something called Redis, which is essentially a fancy version of this. Now, one of the problems, of course, is it's essentially impossible for me to reason about which key goes where. Right? I basically need to evaluate every machine key pair in order to know what goes where. That's expensive if I have a large number of machines. So if I have 10 machines, no big deal. If I have 1,000 machines, well, I'm screwed. But okay, bear with me for a moment, because we'll fix that momentarily. Now, if I wanted to have k replicas, basically, if I want to make sure that a particular record is not only stored in a single machine, such that if this machine dies, well, somebody else will also have it. What I could do is I could just pick the k smallest hashes of key and machine pairs. And again, the rebalancing is really nice, so the entire argument just goes through. Okay, but this is horrible in terms of, reasoning about it. So there's a very neat trick on how you can make this simpler. Essentially, you make it simpler by messing with the hash function. So what I'm doing is, rather than hash of key on a machine being some arbitrary object, what I do is I compute hash of key. In this case, just for mathematical prettiness, I use minus hash of machine mod n. Okay? So what happens now? What happens is that basically, for any given machine, basically for a key, or the set of keys is essentially just offset depending on which machine I use. So what that therefore means is that if I was to sort all the hash of keys in sequential order, I'd see that there is a contiguous range of keys that wins the contest for a particular machine. So now I don't have to actually go and compute for all key and machine pairs what the hashes are. I just go and compute it for the keys once, and then I can find out exactly, minus machine, what's its where. So it's much, much easier. Likewise for k replications, I just have subsequent machines. Now that sounds horribly complicated. Here's a much simpler way of thinking about it. So this is called its distributed hash table. So if you used, Nutella or anything like that, any peer-to-peer client, they will probably use some fancy version of this. I go and insert the keys into a ring. I go and insert the machines into a ring. And what I then do is I basically make the corresponding segment be owned by that machine. So now, if I remove a server, basically segments get concatenated. So I end up paying for that mathematical convenience by the fact that now my load balancing isn't quite as pretty anymore, right? So now, rather than having this nice order of 1/m load balancing, I'll pay a price which is basically going to, because now it's essentially going to depend on the number of machines. So what you'll actually want to do is you want to insert the machine multiple times. We're not going to go into this in a lot of detail. There's a little bit of reasoning in there. You can look it up in a lot more detail. But, okay, let's just go back. But this is essentially how on modern systems keys are distributed. So there's nice mathematical analysis that you can do. There's also nice machine learning that you can do. Okay, so this is how this relates back to machine learning. Not going to worry about storage because we don't have enough time. So you can look up the slides later. But I should probably tell you briefly about MapReduce. MapReduce, who's heard of MapReduce before? Okay. If you haven't, you should ask yourself why. Seriously. This is, I know it's systems, but it's actually kind of important. So MapReduce is basically very, very simple in the form that you take a set of key value pairs. You perform a mapping from each key value pair into something else. And then reduce aggregates all the key value pairs with the same key into something else. Right. So Python, for instance, can do that. So functional programming can do that quite nicely. Now the brilliance of essentially Gemawat and Dean, remember that Jeff Dean from before, is to use this to actually scale it to many, many machines. Because what you basically do is you have workloads, you have thousands of possibly faulty machines. Each of those basically do a trivially parallel operation for map. And then they reshuffle. And then they do a reduce operation likewise. So now if a single machine fails, I just rerun that particular part of the mapping again. There's actually a lot more going on behind the scenes. There's a really cool paper. It's called The Tail at Scale. This is by, again, our friend Jeff Dean and Luis Barroso. I think CICM 14. It's an extremely well-written paper. Super easy reading. I strongly suggest that you read this at some point. The good thing is you can read it while you're tired. This is so well written. But yeah, I still suggest you read it while you're not tired because there are lots of details if you read between the lines. But of course they had to essentially, strike the balance between giving away Google's secret sauce and talking about things. So for instance, so essentially this is all about latency hiding. And the idea is, for instance, when a machine doesn't, get things back in time, you start requesting things from another machine. It's a little bit like when you work on a project, you have, 10 teammates, and one of them is really, lagging behind. So at some point, well, you don't know whether he's actually going to come through or not. So at that point, you might actually ask somebody else to maybe start working on the same problem as well. But you don't want to do that unless that person is really lagging behind. And the same reasoning essentially can be used for machines to hide long delays and other things. Okay, fine. So MapReduce is very, very simple. The simplest case, so for instance for word counts, you could have the mapping function taking documents with maybe some document ID. So we're not going to use that, we're going to throw that away straight away. And we basically emit a list of many word and count pairs. So this map operation doesn't have to be one-to-one. It could take a document and shred it into many word count pairs and emit that. So now I have a lot of tuples. Now the reduce has to go and aggregate all those word ID and count pairs for a given word ID to the same machine. So there's a lot of engineering going on behind the scene. And then now, afterwards, the reducer has actually a very easy job. It just sums everything up for that particular count. And then it emits a word ID and aggregate count pair. This is about as simple MapReduce as it gets. So there was this cool paper by, essentially that came out of Stanford, Andrew Ng and co., which basically argued that all of machine learning is MapReduce. Well, it's not, or at least if you do that, it's hideously slow. But it was a very nice insight that a lot of the algorithms, at least in principle, could be made trivially parallel. And the idea is, well, you compute gradients on subsets of the data each. That's my map phase, right? I basically take all the data and aggregate the gradients. I then emit the coordinate and gradient value pairs. And then in reduce, I just add all the sub-gradients together from different machines. And so I get an overall gradient. And once you have a gradient, you can take an update step and you keep on doing this. Right? Likewise, k-means clustering, you could do the same thing. And you would basically have to iterate between map and reduce phases. Can somebody tell me already what might be possibly going wrong if I iterate over map and reduce?
You're like transferring lots of memory between machines, which could be bad if you have lots of memory.
Awesome.
Data.
So this is already one of the problems. Basically, you're abusing your hard disks as your network interface. This is never a good idea, right? It's a good idea for fault tolerance, but it's a really bad idea if basically if you're turning your hard disks into the bottleneck. There's another problem. It's related to that one. Any other suggestions? Well, basically, a naive implementation of MapReduce, as in if you use Hadoop, essentially forgets everything about the mapping and about the reducing every time it runs through. So the problem, therefore, is that each time you process the data again, the system is completely dumb. It has forgotten all the state. You have to build up all your auxiliary data structures and everything again, just to then, remove it again and throw it away. This is like, you're doing malloc free on the same memory location, but just at the system's scale. This is extremely wasteful. And that's essentially why MapReduce can be hideously slow, because you have this monstrous overhead from the systems of actually, MapReduce first needs to actually get the machines. It then needs to get the data to the machines. It needs to do stuff. And so this can be minutes. So now if each operation takes minutes to step through, any algorithm that uses a lot of MapReduce iterations is garbage. So, maybe 5 or 6 steps is okay. Once you're starting to look at 20, 30 steps, you probably know that you've done something wrong. Okay. And this is exactly where all the modern machine learning algorithms at the system side, depart. Namely, they try to have some degree of persistence in the iterations. I'm not going to walk you through the details of MapReduce, except that, this is exactly what I talked about before. Map basically computes grades on subsets of the data, and reduce adds them up.
What is embarrassingly parallel?
Oh, embarrassingly parallel is essentially the code where the solution to parallelize it is embarrassingly simple. Okay. For instance, let's say I want to compress a lot of files, and I have maybe 1,000 computers. The embarrassingly parallel solution is every computer gets a certain fraction of the files, and it does its job, and it's done. So, in other words, there is no engineering, no thinking required to actually parallelize that. So, embarrassingly parallel is a fancy way for saying the solution is trivial. Okay. Now, as we all know, there's a new game in town. Rather than MapReduce, there's Spark. And essentially, the neat thing about Spark is that rather than having map and reduce, it has a much richer language for what it can do, and it has some degree of persistence. Right? And so it's way better than Hadoop. Well, it's not even funny anymore. So at least you can design this. that's it. None of those algorithms are really state of the art compared to what you really can do. Okay, so that's the little grain of salt. So what you should do is maybe something like this. So this is basically what we've been doing for the past year or two. And I mean, there's a couple of other things you could do. There's something called, for instance, GraphLab. But essentially, the key insight is that a lot of models, a lot of machine learning problems only have a small number of different data types. So the reason for that is that every time you introduce a new data type, a new structure, some engineer probably had to write some code. And engineers don't like doing that, right? Because it's work for them. So therefore, the number of different data types is going to scale with order number of engineers, and you usually have order 1 engineer. But your user base, or the documents that you collect, or the number of pictures that you take, or how long you record stuff, is going to be order n. Right? So this is really important because it's actually good news. It means that we don't really have too many different blocks that we need to actually keep synchronized, that we need to keep analyzed. The second thing is, usually I'll have way more data than what fits into, more parameters than what fits into memory of a single machine. But usually my local working context does fit into a machine. And so what you then do is you basically decouple the aggregation from the data processing. And basically what we try to do is we try to optimize for about 80% of all machine learning problems. So it's not going to be terribly awesome if you have something like loopy belief propagation, or if you have, graph-based algorithms. You need to actually do a couple of other things for that. But for the rest, this actually works quite nicely. And so what you do is you basically bake, steal, and borrow from MapReduce, except that now mappers and reducers can talk to each other in both directions. Remember before that the mappers did their thing, then they passed things to the reducer, then the reducers did their thing, and then everything was killed off again, and that was it. Now what we do is basically we have mappers and reducers talk to each other. So I'm going through this a little bit quickly, but I just want to convey the key idea. And this has been implemented probably about a dozen times by now in different companies. There are even 2 implementations within CMU. Okay, fine. So this is effectively what you'd want. You have a server that talks to multiple clients, and they exchange data. What you can actually do is, this is really what you have to do in practice. So the reason why this thing doesn't work is because, well, actually, can somebody tell me why this cannot be implemented in practice? If I have a single server that talks to lots of clients.
Network bandwidth.
Network bandwidth, processor bandwidth, and so on. So if you think about it, right, so if, I wanted to teach a class for 400 students. If all the 400 students wanted to talk to me, there's no way I could handle it, right? I'd probably need a team of TAs. And so what would happen is that now, by adding TAs, I can scale up my bandwidth, right? Because the TAs talk to different students, and those different students maybe talk to multiple TAs for different aspects, right? Maybe one handles their programming, the other one handles maybe their math, and so on and so on. So by doing this, I can actually scale things up to very large classes, or in this case, large numbers of machines. But if I was just the only one handling a class of 400, well, I would get completely swamped. None of the students would really get any time out of me, because I could probably just say, hi, and then next student, please. Right? And that would be just an hour of office hours. And likewise here, the processor would be completely overwhelmed. Network would be completely overwhelmed. Right? But if I have a bipartite graph, this doesn't happen. Yes?
These masters all do the same thing?
They do something that's very similar to the same thing. So for instance, what could happen is that they update different coordinates of a common parameter vector, right? It could happen that they sketch a different subset of keys. So the idea is that this works whenever your problem can be decomposed in such a way that each master can more or less act independently. If that can't happen, then I may have to go and add another layer here. You can just add another bipartite graph here and you can compose it. So here's what really happens in practice. This is actually what's implemented in the parameter server. You basically have groups of worker nodes which may very well do different things. One could be serving ads and the other one is building a new ad serving system. And they all talk to the server nodes. You have server managers which basically make sure that if machines die, things get reallocated. And then remember all this replication stuff and so on that I talked before. This is exactly what happens here. You basically have a key that's owned by a particular machine, but then it's replicated and replicated again. So I don't have time to walk you through exactly all this stuff. And yeah, it's actually already 11:50, so I can't really show you the varied details anymore, except that, yeah, this is quite effective. So this is basically how you can make things run on large amounts of data, 1,000 machines, half a petabyte of data. So look through the slides. There'll be a lot more pointers in there. Yeah. Basically, that's the end of the scalability lecture. I think this is actually right now one of the most exciting parts of machine learning. How to take algorithms and to scale them up to large amounts of data. Because there are non-trivial mathematical challenges in there, right? This is not just, so to say, grease monkeys hacking code. This is actually analyzing, proving that this code is meaningful, analyzing its statistical properties, proving that it will not fail. So there's space for theorists. This is not just for hackers. So make no mistake, this is these are interesting intellectual problems that you're going to solve. It's not just writing code. Okay, and that ends the class for today. Any questions? Will you please press stop? Any questions?